this is Algebra Lesson 7-6. Systems of linear inequalities, I should say, not linear equations, I should say inequalities. That's an error. Systems of linear inequalities are two or more linear inequalities together for which a common set of solutions is sought. A solution is a system of linear inequalities is the solution or the set of solutions that makes the system true. In other words, it's where the shading for each type of graph overlaps itself. The last lesson we learned how to graph one linear inequality and shade one side of the graph or the other. In this lesson, we're going to learn how to graph two and how do you shade so that you know where the solution of the system is. Now, your steps to solving systems of inequalities is that you first graph the first inequality with a proper boundary line and shade it in one color. Step 2 would be to graph the second inequality with a proper boundary line and shade it in a different color. And then where the shadings overlap, that's the coordinates where it would be a solution to both systems. If the shading never overlaps, then it would be no solution. All right, let's solve these by graphing. We have this first equation here, where we have y is less than x plus 3, and negative 2x plus 4y is greater than or equal to 0. I'm going to solve both of these by solving them for y equals 2. The first one's already in, y equals. And now that we have two inequalities, let's just number them 1 and 2, because that'll be so much easier to label on our graph as well. It'll take up less space, and we'll be able to read our graphs much more neatly. So this first graph here, if I was to put my x and y axis, there's my y axis. Y is less than negative x plus 3, so it goes through 3, 1, 2, 3. Down 1, right 1, down 1, right 1, down 1, right 1. This is a dashed boundary line. So I'm going to make sure I dash my boundary line. Okay, that's pretty decent. So here we go. It's nice and the way it needs to be. And there's two ways you can do this. You can shade it, or you can tell me where you're going to shade it. I'll shade this one, and in the next one I'll tell you where I'm going to shade it and show you what the difference is. So there's my first inequality. If I tested 0, 0, 0 is less than 3. That is true, which means we should shade this inequality down here. Okay, that's nice and shaded. That works pretty well. Don't shade so close to your boundary line that you can't tell your boundary line's solid or dashed. The second inequality, I need to solve for y equals. I can't use intercepts because I only get 1 point no matter what I do. If I put in 0 for x, I get 0 for y. And if I put in 0 for y, I get 0 for x. So you can't use the intercepts. So I will have 4y is greater than or equal to 2x divided by 4, divided by 4. Y is greater than or equal to 1/2 x. So that's easy enough. Starts at 0. 1/2 means up 1 over 2, up 1 over 2, up 1 over 2. Too many dots, I mean, close to my graph. So up 1 over 2 is here. All right, so now I'm going to have another line. This line is going to be solid. So I'm going to put this one in a solid line. And I'll just use this guy here. I'm going to use a solid line that goes through this. Extend it a little bit. Make sure it goes through my points nicely. There we go. Looks pretty decent. Lock this in place. There's that line. Now I can't use 0, 0 as my test point because it goes through 0, 0. So I have to use a different test point. I'm just going to use negative 2, 0. Okay, I can test negative 2, 0 pretty easily here. Negative 2, 0. If I put in negative 2, I'm going to get 4. So I have negative 2 times negative 2 plus 0 greater than or equal to 0. 4 is greater than or equal to 0, so that works. So I'm going to be shading where negative 2, 0 is. And that would put negative 2, 0 is here, so that's going to be up this side of my graph. Now the solution to the graph is where the colors overlap. which in this case I'll highlight it so you can see it. I'm pretty sure you can see it, but just in case you can't. That would be this section right in here. That's where the two colors overlap. This can get really messy doing it this way. So I have a different way that I like to do it, and I'll show you that in the next problem. Okay, the second problem here, 2x plus 3y is greater than 12, and 3x plus 2y is less than 12. I can use intercepts. Very, very simple to use intercepts here. Again, I'm going to label my equations. Equation 1, equation 2. In equation 1, I use intercepts. If x is 0, I have 3y equals 12, so y equals 4. If y is 0, I have 2x equals 12, so x equals 6. In equation 2, if I use intercepts, if x is 0, 2y equals 12, so that's 6. If y is 0, 3x equals 12, so that's 4. So my x-intercept for graph number 1 and my y-intercept for the graph, let me draw my x and y-axis really quick. Y-axis. So if I'm going to solve my intercepts, my x-axis in equation 1 is at 6, so it crosses the x-axis at 6. 1, 2, 3, 4, 5, 6 here. It crosses the y-axis at 4 here. So there's my first graph, and of course it is a dashed line. So I'll go with my dashed line here. Straighten it up a little bit. It goes where it's supposed to go. That's why I love to really use a ruler on the smartboard. It gets better eventually. There we go. That one's pretty accurate. So I'm going to lock that in place. So there's my first one. And if I was to test 0, 0, I would have 0x plus 0y is greater than 12. 0 is not greater than 12. Now here's where I told you I don't like the extra shade because it gets really messy. So I just draw arrows. And in my particular instance, I know that greater than 12 in this place is going to go this direction. So I'm just going to tell myself I would shade this direction in this graph. And this is graph number 1. For graph number 2, I'm going to plot the point. It crosses the x-axis at 4. 1, 2, 3, 4 here. Crosses the y-axis at 6 here. I'm going to draw another line in. It's going to be a dashed line. This time I'm going to put it in black just so you can see the difference between the two lines. So I need to go through this point here and this point there. And I'm going to straighten that up a little bit. There we go. That side looks okay. Here, there we go. That's pretty accurate. So I'll lock that guy in place. So there we have that. All right. Now we're going to test 0, 0 there. 0 is less than 12, which is true. So in this particular graph, I would be shading this direction. Where is it that the arrows point at each other? Right here. And that's where I would shade. That way I only have to shade one color, and it's not quite as messy as that. The first graph here is really, really messy. The second graph for me is a little bit neater. I need to make sure I label both my equations at equation 2, and there you have the solution to your system of equations, or inequalities, I should say. Let's work on a word problem. Suppose you have two jobs, babysitting, which pays $5 an hour, and sacking groceries, which pays $6 an hour. Now, you can't get hired full-time at either one because you're a student, and you need money, so you have to work at both jobs. Even though one job pays better, you might get more babysitting jobs, so you'll actually earn more money babysitting. You can work no more than 20 hours per week, but you need to earn at least $90 per week. How many hours can you work in each job? Right? So again, we have to define some variables, just like we always did before. I'm just going to make it easy. I'm going to let x equal hours babysitting. And I'm going to let y equal sacking, hours sacking. Groceries. We have to have two inequalities here. One is going to be based upon the number of hours that I'm going to work, and one is going to be based upon how much I get paid. So one inequality based on time, and then second inequality, one inequality, based on pay. So if we keep that in mind, if I earn $5 per hour sacking groceries and $6 per hour and I have to earn at least $90, that will be the paid one. So let's look at the one with time. I can work no more than 20 hours per week. So for this first equation here, the hours I work babysitting plus the hours I work sacking groceries, I cannot be more than 20. I can be up to 20, so it's less than or equal to 20 hours. So there's an inequality based completely on the amount of time I can work. Then I can do my second inequality based upon how much money I can earn. I earn $5 an hour babysitting, so 5x. I earn $6 an hour sacking groceries, 6y. And I must earn at least $90 per week, which means greater than or equal to 90. So there's my two inequalities, very simply put. So I have two inequalities. They both can be solved using intercepts quite nicely. So I'm just going to move this up just a little bit. Inequality number one, if I do intercepts, if x is 0, y is 20. If y is 0, x is 20. That's really simple. The second inequality, if x is 0, 90 divided by 6 is 15. And if y is 0, 90 divided by 5 is 18. Now, obviously, I can't count by ones on my graph, because that's probably not going to fit. But I also know I don't need anything past quadrant 1. So I just need quadrant 1 here, so I'm just going to leave that so I can label it. Right? Since I have to go all the way up to 20, and I don't think I have 20 squares on this graph, 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Nope. I'm going to count by 2s. 2, 4, 6, 8, 10, etc. That way. Then I'm going to count by 2s the other way. 2, 4, 6, 8, 10. And I can graph a fairly accurate graph this way. So, equation number 1, my x-intercept is at 20. So I'll cross the x-axis at 20. So it's 10, 12, 14, 16, 18, 20, right there. Crosses the y-axis at 20, 10, 12, 14, 16, 18, 20, right there. Right, so there's that line. And since it says less than or equal to 20, I know that 0 is less than or equal to 20, so I know I would be shading on this side of this graph. This is equation 1. Equation 2, I'm going to grab 0 and 18. It crosses the x-axis at 18. 10, 12, 14, 16 right here. Crosses the y-axis at 15. 10, 12, 14, 15 is going to be right here between 14 and 16. Again, draw my line. That's a terrible line. That's a really bad line. That's equation 2. Right, and that would be greater than or equal to 90. So 0 is not greater than or equal to 90, so we know we can go this way. So really, the region is bounded by the boundaries. So really it can go only to the x and y axis, but shaded in where I have here. Don't shade here. Do not shade up here because it can't go past the x-axis or the y-axis because you can't have negative numbers. So now it says how many hours can I work at each job? I can choose whatever I want. Okay, I can sit there and choose how many hours. I just need to choose something that's in this region. Like maybe I'll choose this point right here. It seems to be smack in the middle. So I can do 8 hours of babysitting, okay? And I can do 12 hours of sacking groceries. So I can do 8 hours of babysitting, 12 hours of sacking groceries. And that will make me more than $90, but less than or equal to 20 hours. Okay? That's how you do an inequality with a word problem, with a system. The last thing we need to do is we have to be able to write a system of linear inequalities for a given graph, which really isn't that complicated once you remember how to write an equation. Let's, just for the sake of making these easy, let's count these and call them 1 and 2, just because it'll be easier to refer them back to them this way. So this is going to be equation 1, this is going to be equation 2. Inequality 1 and inequality 2. If it's a horizontal line, hopefully you remember from Mr. Slope Guy that a horizontal line has a zero slope and it's at y equals. So we know y. We know this is at -2, and we know that it's shaded above the dashed line, so it's got to be greater than -2. So there's the equation for the inequality for number 1. Number 2, we're going to do something very similar, except for now we have to look at it. And let's remember that y equals mx plus p. Let's figure out our slope and our y-intercept. Let's figure out our slope first. I'm going to pick this point up here, and I'm going to keep counting until I get down to this point down here. So that's 1, 2, 3, 4, 5 units down, and 1 unit over. So my slope is -5. I can clearly see it cross my y-axis at 3. So I can put it in y equals mx plus b form, but I have to replace the equal sign with an inequality. So we'll just leave it blank for the moment. Now we just have to figure out which inequality we need. Is it greater than or equal to, or less than or equal to? It's got to be an equal to because it's a solid boundary line. If it was not an equal to, it would be a dashed boundary line, which is why we use the greater than symbol for the first equation versus the greater than or equal to symbol. Okay, I'm going to assume that it doesn't go through 0, 0. So let's just put in a greater than symbol. If I put in a greater than symbol, I need to test something. Let's test 0, 0. 0 is greater than or equal to 3. That's false. So I would not shade where 0 is. It is not shaded where 0 is, so that actually makes this inequality true. So there's my inequality. Y is greater than or equal to -5x plus 3. So there's the two inequalities for that system. We can do the same thing here with problem number 2. I'll label this one number 1 and this one number 2. In equation 1, we'll figure out our slope and we'll figure out our y-intercept. And in equation 2, we'll do the same thing. Figure out our slope and we'll figure out our y-intercept. In equation 1, my solid line. If I look at this, I can see that it's going down 2, right 1, down 2, right 1, down 2, right 1. So my slope is -2 over 1. My y-intercept is at 3. So I have y, I'll leave it blank, -2x plus 3. Now I need to figure out if it's greater than or equal to. If you haven't figured this out by now, most of the time when you're going this way, it's greater than or equal to, or greater than. If you shade on this side of the graph, it's less than or equal to. So greater than or equal to. Then I can test a point. If I test 0, 0, 0 is greater than or equal to 2. That's false. I didn't shade where 0 was, so yep, must be a true statement. Right? So now let's look at the second one. If I look at my dashed line, I can see that my y-intercept is right here at -3. The slope is a little harder to find, but you can still do it. I'll do it in blue so you can see it. I'm going to go up here and over here. So I went up 1, 2, 3, 4 units and over 1. So 4 here and 1 there. So my slope is 4. So again, y, we get inequality out of it, 4x minus 3. On this one, we're shading to the left of the graph. So it appears that it should be less than. Notice it's not an equal to because it has a dashed line. Now let's test it. Let's test 0, 0. 0 is less than -3. 3. That is false. So we would not shade where 0 is. So that's not right, is it? If we look at that, if I look at this for just a second, if I'm looking at this graph here, if I leave the less than symbol in here, let me pull the graph down just a little bit more. If I leave this, I'm going to have 0 is less than -3. That is false. So I would not shade where 0 was. If you look at the dashed line graph, they're shading on this side of it, so eventually they're going to get where 0 is. So it has to be flipped around, doesn't it? So now we need to flip our inequality symbol to the other direction. So it would be y is greater than. If I looked at the greater than, I would have 0 is greater than -3, which would be true, and eventually we are going to shade where the 0 is. So here's our two inequalities. There's the first one. Here's the second one. So that's solving systems of linear inequalities.